на YouTube. Okay, I think now we are on the YouTube, so we can start. So the plan for today was when we discuss a concrete example, quantum affine SL2. So the name of the course is Affine Quantum Groups. In the first lecture, we had something about quantum groups, and we had something about affine algebras. But we have no affine quantum groups. So actually, the last time we didn't finish the story about affine groups, but I decided that it's already October, so I should start the topic. And actually, the first main theme about affine quantum group is the presentations. So maybe before I start example, which will I say a few words about the general picture. And the first thing to take away from the story about the affine quantum group is that they have at least 3 different presentation realizations. First is a Drinfeld-Jimbo type presentation. So what do I mean by the word Drinfeld-Jimbo? So we have generators E, F, and K's, similar as for finite dimensional case, but now we have another Kac-Moody algebra. So we have quadratic relations between E's, between E and F, K with E is computed in standard way, and so on. But the only difference is that now the Cartan matrix is larger. It is, to be very honest, R plus 2 dimensional. Or we can, if you talk about G tilde or G, if you talk about G hat, this R plus 1 dimension. It is degenerate. So as for any Kac-Moody algebra. Another presentation is called New Drinfeld. This name is because Drinfeld wrote a very short paper with the name New Presentation of Yangian Quantum Affine Algebra. And this is, I mean, this paper is more than 30 years ago, so this presentation, of course, is not new now in any sense, but it is called New Drinfeld. But to have some idea in head, this is a presentation is a form of loop presentation. So if in the first case we have generators E0, ER, K0, KR, F0, FR. So in this case, we have generators will be given in terms of the currents. We have some X plus 0. Okay, so let me write it in this way. K plus minus of Z1, KR plus minus of Z, and X minus N. Okay, let me skip a bit what goes on with case, because other parts I wrote in mode, and here it is a bit more tricky. But and when I talk about currents, I mean the following. So I can take X, the current Xi plus of Z is a generating function of the generators. And similarly for minus.
А там
Questions?
прям то же самое n, что и без движки на единицу, да?
Yes, yes. Of course, that's a matter of the definition. But when you define, usually use current for the affine algebras, here is usually n minus 1. But in QD format case, there is no such shift. Just so in this definition, we think about affine algebra as a Kac-Moody algebra, and in this definition, we think about affine algebra as a loop algebra. And again, we should write down some generators or some relations. And this is what Drinfeld did and what we recall later, what we defined. So this occurrence, how to say so, the word vertex separator appears in this setting, but we will not have. I think there is still no good notion of Q deformation of the vertex algebra. So there will be no vertex algebra and no operator state correspondence and so on. But the technical things, the calculations which we will do, will of course resemble the vertex algebra. So we actually will consider examples of the Q deformation of vertex algebra, but without such words. Other questions?
Okay. Sorry, this operator is acting on module, so it's finite or not?
This generating. So here this generators of the algebra. So this is just the infinite sum of the generators of the algebra. Then, if you want to act this on the vector sum representation, you should. This requires some care. So representation should be such that the sum is finite, or the sum should be convergent in some sense, or something like this. So action of this operator requires some care.
Oh, okay, thank you.
Okay, and third presentation is, I will call it a parallel presentation. And it says that we have matrices L plus of Z, L minus of Z, and relations of the form R of Z over W, L plus 1 of Z, L2 plus of W is equal to and relations like this. And this L plus L minus are these are matrices with coefficients in our algebra. And this R is a finite dimensional R matrix. I mean, those who were in my course last year remember that we discussed such presentations for not affine GLN. And this is the names here: Fadeev, Rishtikhin, Takhtajan. I'm not sure about spelling. I will correct it in the notes. And in affine case, there is also a paper by Reshetikhin and Semyonov Tianshansky. And also, so that in order to give the standard definition, we don't need much. We don't have to do much work. So we just take the standard formulas from Dinfeld-Jimba. The difficulty, for example, is to prove that this relation is equivalent to this presentation is equivalent to this presentation. I will give. And the existence of third presentation, new Dinfeld presentation, is a new feature of the affine quantum affine algebras corresponding to quantum finite dimensional algebras. Of course, it is expected such because the ordinary affine algebra have two presentations. The problem to prove that these presentations are equivalent, so we have one definition, another definition, it is a problem, is not easy. And I think if I will try to do this in full detail, this will take maybe all remaining time as a course. So actually, I will plan to spend this and next lecture in the discussion of the SL2 case, and then I will have some remarks about history, references, how to do this for any finite dimensional algebra G or any quantum affine G hat, or starting from finite dimensional simple algebra G. So from now on, today we will talk about SL2, and next time we also talk about SL2. But just to have in mind this picture, this is what we should expect. We should expect to have 3 different presentations of the one algebra. And maybe one last remark, that there is some sort of, how to say, common, I don't know, informal remark. So informal remark that if you want to prove something non-trivial about quantum affine algebra, to use them somehow non-trivial, then you have to use at least 2 of these presentations. So there's not sufficient conditions, but formally that's necessary because the links between any of this presentation is quite non-trivial. Okay, if no more questions, then we'll go to details about this. Do people on Zoom hear me well?
Yes.
Yeah.
Yes.
Okay. Let's talk about
Misha, sorry, I just want to ask about your last remark. Can you please repeat? You said that if we want to prove something, then we should prove using 2 different presentations.
You want to use quantum affine algebra somehow non-trivial to have deep result about the quantum affine algebra. You should use different presentations.
Meaning that you should combine 2 methods at least,
yes,
maybe 3.
Yes.
Okay, I understand.
I mean, this is just, at least this is what Cherry Presley said. Okay, as I said, the easiest way to start is Dinfeld-Jimba presentation. We have generators E0, E So this is Kaplan matrix of quantum affine SL2. We have 2, 2, and -2 here. And this Kaplan matrix appears in the relations between Cartan part, K0 and K1, and our generators E and F. So we have this, such relation. So it means if I and j are equal, then we have q squared, and I and j are different, we have q minus 2. And these relations I just copied. And this is also, so all this is the same as we have in finite dimensional case, but the difference is we have a fine algebra. And this is theory relation. Here we see the first difficulty, which is because affine SL2 is not simple late. So theory relation is not cubic, but now quartic. these numbers are quantum 3, Q deformity number 3, and maybe this is all. Everything is, we have symmetry which permutes I and J, so we have, I wrote one relation just to add I not equal to J. What? Yes, this, I mean, maybe it's a matter of the which word we put. When I say simple laced, I mean that we have in the diagram, we have two nodes which are connected not by one arrow. We have two arrows.
So
but it is good in the sense that the lengths of all roots are equal, not real roots. So we don't have to work with two different Qs. In this case, this is still simple story, but formally not simple laced.
And for SL3, for example, we again will have of the
cubic serial relations.
Yes.
Yeah, so in this sense, SL3 will be simpler, and sometimes even people in papers say that we prove for SL3 and for SL4. SL2 we don't know because of such difficulty. But for what I'm going to do, this, of course, this will lead to some complications, but simplifications of the SL2 will be more important for us. So that's why I decided to spend more time about example. So, other questions? Everything is clear. Here is the formula for the coproduct. I just copied it from the first lecture. This is why it is written already. Now this matrix is degenerate, and it leads to the fact that the product of K0 and K1 will commute with any other generator, with E and F. So this is a central extension, if you want. And this is more about the SL2 hat. If you want to speak about just Kac-Moody algebra for the definition in the Katz book, one have to add D, operator which differentiate, and it acts by 0 on the generators correspond to not affine part, which is denoted by E1, F1, and K1. And E0, F0 are eigenvectors for it with eigenvalues 1 and -1. In terms of the root formula, I should correct my picture, but so E1 lives here and E0 lives here. So this is why E0 have eigenvalue 1 and F0, which lives here, have eigenvalue -1. Maybe another way to say it, E0 is minus x minus theta times t, has t first power. When as usual in quantum groups, we actually have not the algebra generator. At least in this presentation, but there are Q powers, so we have to replace Q by Q in power D, or even one can add the full group of the elements Q in power alpha D, where alpha is a complex number, and the relation between them and other generators will follow from these relations. Yes, this is a misprint. Here should be to 0. Okay. It can happen in other parts of the slides also. So one of my references, people use K2 instead of K0. So maybe for this reason, or I don't know for which, I make some mistake quite often. Okay, if no more questions, then let me recall what we talked last sometime before about while group. because we will use it. So affine extended while group is generated by simple reflection S0 S1, which correspond to roots, and also automorphism tau. Here is a picture. So S1 and 0 are reflection with respect to this actually points, this affine group, and its affine representation. And we have more other roots and reflection with respect to them. And there is also automorphism, which preserves fundamental alcove, which is this segment. And clearly, this is a reflection with respect to the center of this segment. And this reflection is denoted by tau. This reflection permutes these 2 points. So it permutes reflections S1 and S0. So we have tau S1 tau inverse is equal to S0. Here we have formula which should be corrected in order to look better. And each of these generators is just reflection, so it is involution. As I taught sometime in last lecture, that in this group we have a subgroup of translations. In the affine, not extended affine group generated by S0 S1, this group correspond to root lattice. In the extended, it will be weight lattice. So we have to, and the generator is S0 S1 and tau S1. Indeed, composition of S1 and S0 is a translation by this vector, which is actually alpha, which corresponds to simple root. And this composition, S1 tau, is a translation by this vector, which is, I don't know, is fundamental weight. So we have weight lattice. And this one have one generator, so the whole group, whole translation group has this form. Are there any questions about this reminder? Okay. There is action, but on the Dirichlet-Jimba group, the action is given not while group X, but actually it's big extension, P group, which have surjection to the Y group, but this not appears in the quantum group case. Actually, just braid group X. And the braid group defined by the similar relations as here. But we don't have, in this case, we don't have braid relation. Maybe I should write it. No braid relation. We don't have braid relation here. The composition of S0 S1 has infinite order. This is because of the not our algebra, our root system is not simply laced. All root has the same length, but not simply laced. So we have just simple relations which involves this external automorphism. So after the conjugation of tau 0, we have tau 1, tau 1 have tau 0, and this tau is still have order 2. So I exclude these two relations. That is 1 0 square and 1 square is equal to. And in this group, we also have a translation subgroup. I defined it already for P. We take just braid analog of this formula, tau, tau 1, and power n. So let me note that for so this is a procedure which was stated last week. So for positive n, we just take the affine analog, braid analogs of the generators, and for negative n, we take the minus generators. For example, for finite dimensional case, For braid group case, we have, what do I mean? We have, if we take tau as one inverse, then it's equal to S1 tau or equal to tau S0. But in braid case, tau T1 inverse is equal to T1 inverse tau, or if you want tau Tz inverse. So we do not have such elements like tau T0. We have tau T0 inverse we have in our group, but not this one. So actually there is another choice, this choice of the translation subgroup in the affine braid group. So when I write this formula, I actually made some non-canonical choice, and we will see it in our construction. We will see it at some point. I hope I will show it where it is important for. Questions? Good thing about SL2 is that the translation group is generated by one element, so we don't have to check any commutativity. This group is commutative. Let me change the title of this slide. So this is actually the last slide, which was at least partially written before later. We have to define root generators. What do I mean by this? So if you want to have a loop presentation, which we will have, but later, we have, so before we have generators which correspond to simple roots. Alpha 1, and here lives alpha 0. Maybe I can write alpha 0, which is equal to delta minus alpha 1. We have a generator here, 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 and here. Maybe I can show this. We want to define generators which will correspond to all other roots. In order to do this, it's natural to use braid group action, because it acts by automorphisms on. It acts as an automorphism on the quantum affine algebra. T0 and T1 acts by Lustigs as Lustig automorphisms, and tau is just permutation: E0 1, F0 1, T0 T1. Okay, let us make the first important definition. Let us define E alpha plus and delta to be tau T1 in power minus n applied to E1. And E minus alpha plus and okay, and delta to be tau T1 in power n applied to 0. And here is n is non-negative, here n is positive. So where are these generators? Alpha plus and delta is a root here, alpha plus 2 and delta here, and so on. So actually here I am define generators which lives in this part. Say it again. Yes, you're right. You're right. Maybe I should write here n plus 1 and then we will also have a non-negative. Okay, I'm
Я
still.
что-то не очень понял. А вот здесь альфа это либо альфа 0, либо альфа 1, или что это такое?
Alpha, alpha is alpha 1.
О. Сейчас, ну,
Is the root of the not affine the algebra.
в смысле, что, окей, то есть, ну да, это альфа 1, и тогда можно, да, любой. И тут написана формула только для того, как получать первую и вторую и последнюю колонку, вот, которая посерединке, а ее надо действовать все-таки чем-то.
Yes, yes. So here I obtained this and this generators. I cannot obtain using the braid group. I cannot obtain these generators because they are imaginary. They correspond to me as they belong to different orbit of the braid group. So I have to do something to obtain. What is important? I mean, what I want to stress here is that here I use some choice of the translation generator. So I apply the same translation in this column and in this column. So not to have my story somehow consistent. And maybe one more computations. So, for example, so why do I pick this formula? So, in terms of the root, I wrote here that the root alpha plus delta is tau S1 of alpha. Indeed, if you apply tau, alpha 1 goes to alpha 0. And then if I apply S1, this is just reflection with respect to this line. So it goes to here. So tau goes to here, and then S1 goes to here. And in this form, I wrote, so inverse to this is tau 1 inverse tau. So this is a braidization of this element of the affine variable. Other questions? Okay, assuming that this definition is somehow modified, we have the following question. How to define E delta? How to define root generator which will correspond to the imaginary root? Are there any suggestions?
Ну, можно попробовать взять какой-нибудь коммутатор. Может быть, коммутаторы, Q-коммутаторы, там корней, которые находятся с одного боку и с другого.
So the suggestion in Zoom is to take some sort of Q commutator. Vanya, do you have the same? But which Q commutator? Q commutator, Q square commutator, Q inverse commutator, how to pick one? What do you suggest? Of course, we can as a remark, we can say that, okay, let me recall that we defined, I hope I used, let me look to the first lecture and double check that I use the same notations. So here I use notation for adjoint action. So add, okay, let me copy this. So serial relations are given by this formula. So it is natural to think that E delta is given by add Q E1 applied to E0. And this will be what? It will be E0 in E1 minus Q in power scalar product of the corresponding root. It will be Q minus 2. But we don't know. In principle, it could be opposite. It could be Q E0 applied to E1. So, and by the same formula, it will be E1 E0 minus Q minus 2 E0 E1. So the question is how to pick one.
Ну, надо как-то единообразно договориться. То есть мне кажется, что этот выбор, он как-то, ну, похож на то, что там, значит, выбрали на выбор в braid группе коммутативных подгрупп.
Yes. This choice resembles this choice which we made. The choice of the generator in the generator of the translation in the affine braid group. And this should be put, we can put it as a condition. So we want okay, so this was a remark just, and now we want, well, maybe I put it as a new point. So we want that the generator which we picked for the translation, so tau T1 applied to E delta is equal to E delta, or at least proportional to E delta, but better to want, because this translation keeps delta. Let us do computation.
Тау T1. Сейчас тау T1 это же сдвиг.
Yes, so this is translation, and how this translation acts. It shifts.
Е2 дельта должно быть написано, или в начале Е0 я что-то ничего не понимаю.
No. Yeah, this did could look a bit not clear, but how this translation acts on the roots. It maps alpha to maybe the fold. You see here we have positive powers, here we have negative power. So this translation moves alpha below, but alpha 0 it moves up. Delta is invariant under the action of the while group. So if you take while group projection, then delta under the translation delta stays on the point. This column goes down, and this column goes up. And we want to have the same property of the root generator.
Okay.
Thank you for questions. I mean, today I'm trying to do something informal. I do calculations and try to do make explanations. So comments are welcome.
Sorry, I have maybe not question, but okay. So this all these translations. So in larger case, we have translations along the roots, or I don't know, co-roots maybe. It's better to say yes. So here we have translation of
along
alpha.
the weights. I mean, where you mean? What do you mean by translation roots? So translations are identified with root lattice or weight lattice.
Okay, maybe I should skip. I understand in some way. Okay.
There is a formula which I realized due to Vanya that I omitted in the lecture, which probably should be written. That in the presentation in the R+1 dimensional representation, T lambda of alpha is alpha plus scalar product lambda alpha delta. So in terms of the roots, all translations are shifted by delta in the linear representation. Okay, I don't know whether it was related initially to your question.
Yeah, it's almost the same. So thank you.
Okay, now, anyway, we have to calculate. So we have to act by tau t1 to something. In principle, we can write here whatever we want. I don't know. Is it okay for you if I just show you calculation, or maybe we do this slowly? I have prepared. Okay, let me show it. So we want to calculate by tau t1 on some combination of e1 e0 and e0 e1. Okay, let us act. So first we have to find out how this tau t1 acts on each of these elements. T1 on e1 acts this way, and T1 on 0 acts in non-trivial way. So we have OC relation is quartic. So the action of T1 on E0 will be cubic. So it will be this formula which resembles the theorem. Who in the audience will remember what is this E1 two in brackets?
Е в квадрате, поделенное там на q факториал, кажется, или на квантовую q, на квантовую двойку, или...
Yes, so this is just e squared divided over quantum 2. And in a minute, so somewhere here, I will forget about this fancy notation and use just 2 denominator. And tau acts very simply, in very simple manner. So this is the advantage of SL2. We have in translation, we have only one braid group generator, which already is not very simple. I mean, we started from just E0, get some combination of 3 terms. What to do? So we now act by tau t1 on this combination. So here I just rewrote it. So I substitute formula for E1 and for the second, I act by tau. So instead of E1, we have E1, but this is no matter. And now we move K0 to the right. Get this. And here we see what we have to assume. It is very natural to want to have this to be, I mean, it is very natural to want this to be commutator. Because we want to obtain element in the nilpotent subalgebra, which will contain only E's. And this can be done only if we have commutator. Otherwise, we can move F to the right, and that's all. So we have to assume, in order to have invariance, that then actually this minus AQ squared is equal to B. So we substitute this and have commutator. And actually, this condition is precisely one of the choices which we had here. So this condition that we have something which is valid in the translation is lead us to the same formula, of course, but somehow specifies the choice. Okay, so we get this. I don't know. Are there any questions? I mean, why no? Is it clear how I move K0 to the right? Moved K0 to the right.
Сейчас. Я сейчас не очень понимаю, как пронести через Т. Еще раз. У нас там какие-то были формулы для этого. Я забыл.
So what is T0 of E1? E1 is again the wrong. Let me show this on the picture. E1 is here. Alpha 0. It doesn't matter. T0 for E1, it is a formula for T1 for tau T1 of E0. So this is this element. This element has a weight 2 alpha 0 plus alpha 1. 2 alpha 0 plus alpha 1 is alpha 0 plus delta. And now we move K0 through this element. K0 commutes with delta, and on alpha 0 it gives us Q squared. Okay? So if we move K0 through E0 squared, we get Q in power 4. If we move through E1, we get Q in power minus 2. So we get here just Q squared.
Я вас хотел спросить, немножко не в тему, но в смысле, ну вот у нас там два возможных претендента на то, какой надо выбрать, они отличаются друг от друга умножением на минус Q квадрат, да?
No. These two candidates are not proportional.
Да, нет, они не пропорциональны. Хорошо, да, тогда все в порядке. Да.
This is a choice of the Q deformation. It is Q deformation is actually not trivial story. There are a lot of Q deformation of the same formula for the commutator. We have to pick. I mean, in words, if somebody told you the correct formula, then okay, everything's you can check it. But if you want to guess the formula, then okay, maybe it's too. I can stop. I can just show you that I made the computation with big care, and the result is following. So that element is indeed eigenvector for this translation, and this choice which we actually made. Okay, so computation, I ignore the computation which I showed you, and this result. Okay. Before we go further, let me say that there is already something which we can check. So our plan for today will be the following. We introduce generators, which we'll call root generators here, and check and try to write down relations among them. If you write down actually full relations among them, this will lead us to the new Drinfeld presentation, loop presentation. I will be honest, but not too much honest. So sometimes some relations I will skip, something I will just say it can be proven, but at least I want to show you some spirit, to show you something. And currently we're in position to prove something. Okay, let us do it. So first thing which we can prove now is a commutation relation of E delta and this and the other root generators which we defined.
Можно вопрос? А EN дельта, оно будет просто получаться как коммутатор уже, ну, можно подвинуть любой из этих из друзей, либо E0, либо E1 на дельта, на N дельта, а потом взять коммутатор.
Okay, if you want, we can say it now. That of course it's natural to define that En delta it will be E minus alpha plus delta E alpha plus N minus 1 delta minus Q minus 2 so I pick if I want to define this element, I take again Q commutator, but now of this two. But the choice why I pick these two, or but not these two, or some other two, is how made by hand, and we have to show that this doesn't depend on our choice. And we will talk about this later. Yes, you're right. Should be the same power.
еще можно такой вопрос, тоже чуть-чуть не в тему. А вот если посмотреть, ну, вот мы определяем сейчас только верхнюю часть, а вот чтобы, ну, нам еще, ну вот когда мы определяем еще нижнюю часть, нам нужно как так договориться, чтобы каждая, ну, как бы, если мы берем два противоположных корня, то они между собой образуют у QSL2, да? Это получается. Или нет?
So
Ну,
can't
понятно,
we
не
talking only
мнимые
about
корни,
the
а
upper part? Okay, so I mean the question was asked, and I will now ignore it. Later, I will. Maybe not today, but this is a good question to think about if you want.
Просто
What to
я
do?
таким вопросом задумался над SL3, и у меня что-то не получилось правильно соотношение написать, чтобы у меня E1, 2, ну, в общем, ладно.
In QT case or just ordinary Affine?
Ну, в ходе формы, да. Но я не знаю, это, наверное, потому что я чего-то забыл или пропустил, поэтому, наверное, должно было все получаться. Я не помню, обсуждали мы в прошлый раз такое или нет. Вот. Ну, ладно.
In not QT case, the general formula were given, I hope.
Не, в ходе формы. Но для SL3, а не для квантовых. Они для, не в афинном случае, а в обычном, но в квантовом. Вот.
It depends what do you want. So do you want if you okay? Let me ignore this question and
Ну ладно, я лучше...
let's talk about what we can do now. What? The question was how to define what is a good definition of the root generators for the negative roots. There is some issue here, but I ignore it for a moment. Okay. What I'm going to say today will be actually based on the very few computations. I will do only simple computations on the slides, and I will the most difficult I will just state, and the medium computations, the medium difficult I will put as problems. So plan as a standard is following. But let me do at least one simple computation. It's a simple computation to what will be if we compute E delta and E alpha. Maybe I should keep this picture on my slide for some time.
А это тоже куб-коммутатор? Или это обычный? Это куб-коммутатор?
You see, even if it is Q commutator, E delta is imaginary root, orthogonal to any other root. So even in the Q commutator we get 0. So it will be ordinary.
Ну да.
Okay, we had some expectation, but what? Let us compute. This will be computed. Now I just substitute our notations. And E alpha is E1. So it is equal to E0, E1 squared minus what we will have 1 plus Q minus 2 E1 E0 E1 plus Q minus 2 of E1 squared E0. Yes, E1 squared E0. Do you see something in this formula? So this is not zero, and
Ну,
we
она
don't expect.
похожа на это. Она похожа на как бы двойное применение коммутатора.
What is t? So this, okay, let me rewrite it this way. Just very simple rewriting. Okay, because I do simple rewriting, I just copy it. You're right, Vanya, yes. Simple writing will be right here Q inverse and right here to Q. And one more simple rewriting will be to move this to Q bracket. And here, right, E0, E1 in square bracket minus Q inverse. And here again, E1 in quad bracket. And this will be already to Q T1, actually inverse of T E0. Or if you want to Q of T1 inverse tau of E1, or if you want, this will be E alpha plus delta. So this is okay.
Да.
So we proved that commutator of E delta and E alpha. Sorry, I lost this two. I forget this two. Actually, you know this two. Everybody knows this two. This is two which we have in relation of SL2. If Q will equal to 1, then we know commutator between H and E is 2. And this is 2 here. Now we can state this as a lemma. Commutator of, okay, let me change the blue color. Commutator of E delta and E alpha plus N delta is equal to 2Q E alpha plus N plus 1 delta. We don't have much time, but maybe I will wait. Maybe somebody can explain how to prove this. Of course, induction, but how to make the step? Which formula do you plan to use? What we can use, the only thing which we can use is a definition. So this is a definition. And now what we can do, we can take our formula which we computed, if you want base or induction base, and apply this automorphism, tau T1. Then this automorphism preserves E delta and shift this n and this n by 1. Hence, we get the induction step. Is it clear?
Ну, примерно все. То есть можно, если что-то в этом равенстве, можно сделать автоморфизм. Ну да, окей, понятно.
Induction? I don't know. We just apply this automorphism.
То есть мы тогда не могли быть вообще ленивыми и... нет, не могли. Ну, в смысле, что типа... Ну да, мы только верхнюю часть что определили, да, окей.
Okay. Let me show you one more piece of relation, which is not difficult to prove. Mm. So we have E delta, E alpha, which is just E1, and we also have E alpha plus delta, which, if you want, was implicitly written here. I maybe rewrite the formula. So it will be E0, E1, 2 minus Q inverse E0, E1, E1 plus Q inverse E1, 2, E0. What will be, what is their commutation relations? Okay, let me once again copy this picture. In the standard case, so one generator lives here, another generator lives here. What is the commutation relations? Who knows?
Commutation relations между чем и чем нас интересует?
Between this and these generators.
I would say that E commutes with E, yeah?
Yes, in the standard case, they commute. In our case,
В принципе, наверное, по градуировке не могут не коммутировать.
yes, in standard, yes, but in this story, I mean, they do not commute. They could, I mean, it could be that they do not commute, and it is quite easy that their commutation relation should follow from the Serre relation. So this cubic, this is linear, and the commutator will be quartic. So we can have to somehow arrange the commutation relation such that it will lead us to this Serre. So what I'm saying that I'm trying to write E alpha plus delta E1 minus Q and with some power which we have to specify now in the opposite order in order to get something like Serre. So 0. Which power should I pick here? Is it possible to do so? Okay, let us try to. First of all, a leading term which we can divide 1 over 2q. Then in the leading term we have E0 E1 cubed minus the next term will be E1 E0 E1 squared. And here what we get Q inverse to Q plus this unknown power. Okay. If I want to, here's a bracket. If I want this to be Serre, then what is the value of this power? What? Okay, people in the audience suggest me to write here 2. Then this will be precisely 3. This one. Okay.
Правдоподобно.
I mean, maybe if people in Zoom switch on the video, I will see how they react on what's going on, and I will.
I don't know, Misha, maybe it was easy to compare coefficients for E0, E1 in cubic.
You are absolutely right. It will be easier to look to the last term, E0, E1 cubed. This last term, no, opposite order, E1 cubed, E0. This last term, we have this Q in power, actually, now in power 2. Okay. Okay, now in power 2. And this 2 will be multiplied by this 2, and so this coefficient will be equal to 1. So this is a Q deformation of the commutativity which we had before. And this agrees with the notion of the Q commutator, of course, because the scalar product between these two roots is Q. Okay, next statement I put as a problem, but because I don't have much time, but and problem will be to prove similar relation, but for but not for the consecutive roots, but for the roots with longer distance. And the relation is the following: that E alpha plus n plus 1 delta E alpha minus Q squared E alpha plus n delta E alpha plus, and now alpha plus delta here. Minus plus in opposite direction. Is equal to 0. If n is equal to 0, so here n is non less than 0, so in order to have all these roots in this non-negative part, is n is equal to 0, this is precisely the relation which we had, which we proved here. No, after it will be twice this relation, nothing more. So the statement is applying the commutator with E delta and also this automorphism, we can prove this relation also. Okay.
Thank you.
Okay, so this is I put as a problem, but I put as a corollary that for n greater than or equal than m, we have E alpha plus. Okay, we have similar relation. But now with m. And where do I put m? I put it here. Here instead of delta, I put alpha plus m plus 1 delta. Here instead of delta, I again put m plus 1 delta. And here I put okay, is it visible what I wrote?
Mm-hmm.
So when I say corollary, I mean that it is easily follows from the problem above. Maybe the last time in the lecture I asked people in the audience, is it easy? How to deduce this corollary from the problem?
Мы просто делаем следующий мотивируем, и у нас, если мы значит, берем и коммутируем с теми членами, которые у нас участвуют, тогда они вот это слагаемое, мы выпадаем силу.
You think commuting with E delta you can achieve?
Нет, совсем вот этим вот выражением. У нас, ну вот, которое задача. Мы берем коммутируем язык, да, И у нас все слагаемые, ну, как бы, у нас каждое слагаемое состоит из монома, который...
No, okay, anyway, the argument is more simple. We don't have to compute with E delta. Probably you can prove this way, but the argument is more simple. And actually, this argument is used in the problem.
What would be if we apply our tau T1 in
Yes,
some
just
power?
apply translation. We apply translation.
So this is why n is greater than or equal than m, yeah?
Yes, we apply translation power of m minus n to this relation, to the to the power m, to the similar relation with where we have n minus m. This operator just shift all the indexes by the same number. So if we take it will be to take a term, and we get from here, we come from problem to the color. Okay, Ваня.
А если мы все-таки коммутаторы попробуем, мы не получим там, что для любых вообще элементов?
Good point. No, I mean about commutator. So I will explain you why the commutator is a good argument, but for some reason I just don't want to talk about it here. But another point was about any n and m. And I said this is true and this is obvious because this relation is symmetric with respect to n and m. So it doesn't matter. And now maybe it's a good point to introduce currents or loops, loop generators, which I want to, for the first time, and first actually last time I think in my lecture today, but let me introduce e power of z be the sum of n greater than or equal to 0, e alpha plus n delta, z in power minus n. Then this relation, which we showed to hold for any n and m, lead to the following relation in terms of the current. This is the formal generating function of the generators of our algebra. Plus of z plus of w times z minus q squared w plus of w plus of z equal to, I actually wanted to say equal to 0, but it's not really 0, and I write boundary term. It means that this series are series in the negative powers in W. And if we compute some term on the left side with negative powers in Z in W, it will vanish precisely from this relation. But there is term which here we have boundary term. If we take constant here and Z here, then we get Z in power of 1. So this boundary term will be more or less like Z E of W squared minus W E of Z squared. So it will not have Z and W both in negative powers. So this, maybe I draw the picture in order to explain this. I will write this precise formula in the notes and maybe even put it as a problem. So E of Z of E of W is a series, maybe the opposite, in the negative powers. If we multiply by this linear term, we get a bit more on the boundary. And if we take this sum, all the interior part vanishes, and we get some contribution from the boundary, and which should be written here. This is because this is not actually current. This is a half current. because we have here take here summation only with respect to positive roots. If you go to from the half current to the full current, then this boundary terms vanishes. You get just simple commutation relations. This is the first current relation which I wanted to show.
Сейчас, а вот подождите, вот все-таки, сейчас E плюс, вот понятно, а вот E от W, это с плюс, ну, не понимаю, Z на E от W, E там какое?
The same E plus of W, just another variable.
Там тоже плюсы пропущены.
Where? Plus.
Не, справа. Вот она
Yes, on the right side this will be actually also plus, yes. Yes.
То есть я что-то не понял про boundary terms, если честно. То есть в каком смысле это boundary terms?
So if we take product E plus of Z and the plus of W, it will be power series in the non-positive powers of Z and W. This I draw by this angle. Then if we multiply by the linear function, we will get power series where powers on ZW will be non greater than 1. And the claim is that all interior parts vanish on the left side. So if you compute on the left side coefficients in the Z in power minus M, W in power minus M coefficient, it will vanish if N and M are non-negative. And the only coefficients which remained will be coefficients where we have Z in power 1 or W in power 1. And this is actually written here. In this sense, this is a boundary. So we have a series where coefficient. So this is no longer permutation relation. Permutation. We have now current with one variable. Okay, I don't know how.
Misha, if we think about Q to 1, yeah, so it should be something like a affine algebra, yeah.
Yes.
So if we put Q to 1, then this boundary term disappear, yeah. So
yes, I think it disappear. Yes.
So my question is about in the boundary term, Q is somewhere.
In the boundary term, I think there is a factor.
Okay, thank you. So boundary term disappear in Q to 1.
Yes. Boundary term disappears to Q equal to 1 and disappears if we go to the full currents, not half currents. But if you write down those half currents, they're more ugly. The Rindt representation to which we are going, it's written in terms of the full currents, but we will not do it. Okay. Now we have one more preparation here. The theorem that the following conditions are equivalent. Maybe I should add once again the picture. And we can read what's written here. So this is the first time when we started to talk about not about just E delta, but E2 delta, E3, all En delta. And theorem said that the following conditions are equivalent. The first condition that the vectors elements which we defined as Q commutators are invariant on the translation. We check this for P equal 1. The condition A means that they're invariant. They're all invariant. Now the condition B means that we can define the element EP delta as any Q commutator. So here is Q to the power minus 2 commutator as a commutator of any two elements of our root generators, such that the sum of the roots is equal to P delta. And condition C states that this E delta is defined commutative algebra. Okay, any questions about the statement? I mean, do people have wants to me to talk about the proof of the theorem, or go further? Okay, maybe I will go further and I will put this proof and some problems, or write down something. Just I wanted to finish in time. This is maybe I wrote as a theorem, but actually this is rather lemma. And theorem said that A, B, C above holds. So this lemma is quite easy computation, and theorem is not so easy computation. It requires some induction, and this I actually just omit. I can give you a reference, but I will not discuss in the lecture. So this I will either give you as a problem. So this will simple computation, and this not so simple computation. So I think it's a problem. It is sufficient to omit.
Я сейчас не понял, то есть в смысле вот эта теорема, которую надо проверить, что ну, в смысле доказательство второй теоремы просто выбирается один из этих пунктов и проверяется, или что?
It would be good if it was so.
Наоборот, все одновременно проверяется.
Yes. So all these three statements are proven by induction. So in the induction step, I mean, in principle, yes, but the proof, at least which I saw, organized follows. So in the induction step, we use all of them somehow.
Окей, ну, я понял.
What? In which formula? N is an integer number, non-negative. So in that statement is that this formula, I mean, n is here should be everywhere. So here also p is again not also with an n. So this, of course, I can write here. Actually, the statement is true for any n, for any p, for any n. But in this form, this is statements are prepared for the induction. So proof goes by induction by n.
Нет, то есть если так вот, если как вы написали условия, то в теореме А плюс С выполняется для любого n.
Yes. So, for example, now we can state a corollary. That all E deltas which I defined, so EP delta, EN delta, or any commutators, no, maybe it's not so easy. Okay, as stated, but maybe it's not so easy to prove it in the negative time. I want to finish the lecture by some theorem, and we didn't write down all definition, all relations, so we didn't come to the different presentation. So we will do this next time, but at least we already proved something. And I state the theorem, and with it, theorem. Elements of the form E form a basis in U n plus. Here UQ n plus is a algebra generated by E0 and E1. So this is a analog. This is a von Kreberg-Witt theorem for quantum, to at least to half of the quantum affine algebra, but since the triangular decomposition holds for any cosmology algebra, this clearly leads to PBV theorem for the whole quantum affine algebra. Von Kreberg. Are there any questions? So the standard PBV theorem for this algebra means that any element of the universal algebra is a product of the roots or of the root generators. So first I take product of the generators on this line column, then to imaginary column, then to this column. And order here is always somehow fixed. So maybe I should say the remark. So if you remember in finite dimensional case, order comes from the longest element, W0 inside the while group. And here we don't have the longest element, but somehow this longest element is S1 and 0 in power infinity in some sense. So here the order is written. So we have minus alpha plus delta less than minus alpha plus 2 delta less than so on. Then in the middle we have delta, 2 delta, and so on, which can be written in any order because the corresponding elements commute. And then we have alpha plus 2 delta less than alpha plus delta less than. Geometrically, the sort is just counterclockwise order in which we see our roots. I finished with this theorem. I didn't give the proof of the theorem, but it is not now. It is not difficult. So the main difficulty is here. And for the proof theorem, one have to reorder elements. And for example, for E with this E alpha plus N delta with positive N, this is done using this relation. Using this relation, you can either reorder them or move them close to each other. And then again reorder. So this PBV theorem follows from the relation which we partially found and partially I'll give you in full slides. Okay, I'm 7 minutes over time, so questions? Or I just.
Sorry, this form last term is E alpha. Maybe some strange because the first term is no E alpha. I don't know why.
Well, the first term is E minus alpha plus delta, so this is E0 actually. And the last term is E alpha, this E1. Maybe. Is it your question or?
Yes, because I think this form is not symmetric. So
This is simple root and this is simple root.
okay. I have another question. If I want to get n minus, so I just use an involution, just like the classical case. It's right.
We'll talk about negative part in a week.
Oh,
Okay. I mean, there are some issues we'll talk next time.
oh, okay.
Okay, if there's no more questions, let me